This section will be looking at Chapter 2, Section 3 on continuity. Okay, you've talked about continuity probably for years in your math class, but in calculus, we're going to go a little bit further, a little bit more in depth in looking at the definition of what it means to be continuous. So informally, a function is continuous over an interval if the graph can be drawn without removing a pen from the paper. So in other words, are you going to have to pick your pen up anywhere as you draw the graph? So like this is a line. I don't have to pick the pen up to um to draw this anywhere. It goes on a smooth, continuous curve with no gaps or breaks or anything like that in the graph. One thing I do want to mention is when you see a curve, well, I say curve, this is a line, but when you see a graph, keep in mind that even if there's not a point like drawn like this, there are like infinitely many points along this. I couldn't even list all of them if I wanted to. So because of that, as long as there's not an open circle there, it is going to be considered to be defined. Okay, so if we have a place where the graph is broken or disconnected, then it's said to be discontinuous at that particular point. So like for this particular one, we've got the limit. We're looking at this and we're considering what happens here at 2. Okay, so 2 is where we have a gap in the graph. We have the graph is broken there. The reason it's broken is because you can see that the denominator is undefined at 2. So because it's undefined at 2, it turns out if we factored this, okay, so if we factored this, we get one of those factors that cancels. So we actually have that hole that occurs there. So the hole is a point of discontinuity. So in this particular case, we do have a limit because as we come this way and we come this way, think about like if you're bringing your fingers together as you come from both sides, then that does have a limit there. So the limit does exist, but the point is not defined at 2. The function is not defined at 2. Okay, if we look at this one, this is another type of discontinuity. You've got a jump where you're jumping from -1 to +1 in here. So we've got open circles over 0. Okay, so h of 0 is not defined. Not defined. Okay. But if we look at the limit here, the limit is also not defined because if I'm coming and approaching the limit, approaching 0 from the left side, if I'm approaching 0 from the left side, then I'm going to be down here at -1. But if I'm approaching 0 from the right side, then I'm going to be up here at +1. And we know anytime the left limit and the right hand limit don't equal each other, then the overall limit does not exist. And so that's why we see down here that the limit as x goes to 0 of h of x does not exist. So in order to be continuous, what you should be seeing here is that the function has to be defined at the point, but it also has to have a limit at the point, and the limit is going to need to equal the function value. Okay, so these are the three criteria that you need to show when you're showing that something is continuous. So the function has to be defined. Actually, let's start with they've got the limit first. So the limit, the order of this is not that significant, but the limit as x goes to the point in question exists. F of c exists. So this is saying the point's defined. And basically here you're saying that if these two are defined, that the two values for the limit and for the point itself equal each other. So by definition, a function is continuous on an open interval if it's continuous at each point on the interval. So generally what happens is because we can't like list every single point on a curve, we don't focus so much on the points that are continuous, but instead we focus on the ones that are not the points where it's not continuous. So you're going to, in general, be asked to like tell which one of these is not being satisfied in order for the function to be continuous. Okay, if we look at this example here, okay, we want to consider, is the function continuous at -4? Okay, so that's the point in question for this particular slide at -4. So in order to answer that, we've got to go through those three criteria that we just talked about. So the first one is, does the limit exist as x approaches 4? Okay, so let's take it step by step. If we look at the left limit, the left-hand limit is up here at 2. Okay, if we approach from the right, okay, so we're coming in this way. That means we're using this part of the graph here. Okay, so that is actually going to be getting closer and closer to a y value of 3. So since these don't equal each other, the limit does not exist. Okay, and that's enough to say that it's not continuous. As soon as one of the criteria fails, then you can say that it's not continuous there. But let's go ahead, for the sake of looking at this, let's go ahead and answer these. So does f of 4 exist? Okay, so, and that should be -4. Does f of -4 exist? All these should be negatives here. Okay, so if I'm looking at the function value, I just need to go up and see, does it have either a closed circle or a curve drawn across it? Okay, so this particular one has a closed circle on it. So yes, it does exist. Okay, but when I come down to number 3, this can't be true because the limit doesn't even exist. So I can't say two things are equal to each other if one of them doesn't exist. So as far as, is it continuous? No, it's not continuous. The reason we would say that it's not continuous is we would say that the limit as x goes to -4 does not exist. Does not exist. All right, so let's look at the next one here. Okay, so if we're looking at -2 this time, because when I look at this graph, there's several places where there's a break. There's a break here, there's a break here, there's a break here, and there's a break here. So all of these are points of discontinuity, but we have to justify like why they're discontinuous. So if I'm going to look and see, first of all, do I have a limit at -2? Okay, so looking at this, if I approach -2 from the left, that's using this piece here because this is -2, then the y value I'm getting closer to is 5. If I approach from the right, the y value that I'm getting closer to is 5. Okay, so that means that the overall limit is 5. And again, just think about, if you take your fingers and follow this, are you bringing your fingers together to a particular point? If you are, that means the limit exists. Okay, so that limit exists, it exists at 5. Okay, next thing we want to look and see, is f of -2 defined? Okay, well, I go here to -2 and I go up, but there's an open circle there, so it's not defined. Okay, so because of that, obviously I can't try to equate the two things if one of them is not defined. So it's condition 2 in the definition of continuity that fails, okay, at -2. All right, if we look at the next one here, the next point of discontinuity is at +1, okay, because we have a break here in the graph. So if I look at the limit as we approach 1, I may have said -1, the limit, the point of discontinuity is at x equals 1, okay? So if I'm approaching from the left, the y value that I'm getting closer and closer to is 4. If I'm approaching from the right, that means I'm following this part here, then the y value I'm getting closer and closer to is 1. Well, if these don't equal each other, then this is going to have to be a does not exist. And then if I look down here at f of 1, well, I have an open circle here. I have another open circle here. So this one is not defined. Okay, and I certainly can't say these are equal to each other if they're both not defined. So not only do I don't have a limit, but I also don't have a function value. Okay, the last one then, if we're looking at the limit, the discontinuity at 3, okay? We look at the limit as we come in from the left side. That's following this part here. So the y value is getting closer and closer to 3. Okay, if I'm going to follow it in as we get closer and closer to 3 from the right side. All right, so we're going to come down here, or I mean, we're going to go up here and we're going to follow it in. So it's getting closer and closer to a y value of 3. So these do equal each other. So that means that the limit equals 3. Okay, our function value though is way down here. Okay, so our function value is at 1. Okay, so these two things don't equal each other, and that's why it's not continuous. So it's condition 3 in the definition of of continuity that fails for x equals 3. All right, one thing I wanted to mention here, if I'm looking at, say, 2, okay, 2 doesn't have a colored endpoint, but the graph does run across that, and it doesn't have an open circle to indicate a break. So it would be defined. So like f of 2, if we needed that, we would just read it off the graph. So f of 2 is actually 2, okay? Because if I go up and over, then that takes me to 2. So f of 2 is defined. It actually has a limit. So the limit as x goes to 2 of f of x is equal to 2, because if I come in from this side and from this side, I'm going to 2. Okay, and so in this case, they do equal each other, okay, and so it is continuous. Okay, these three little dots mean therefore, so therefore it's continuous at x equals 2. And if we don't have any breaks in the graph at all, then we would say that it is continuous everywhere for all x. Okay, so we've got a few questions here that we want to look at and see, is this function continuous at these points that are listed here? So I want you to pause it and try these. It's really important that you take that time to do that. Okay, if we look at these, first of all, if we look at x equals -4, at -4 it is continuous. Okay, there's no break, so it is going to fulfill all three requirements for continuity. If we look at -3, okay, the limit as x goes to -3 does exist. Okay, that limit is equal to 3. But f of -3 is not defined. Okay, so we make it to the second step. First step's good, second step's not defined. All right, if we look at the next one would be -1. And -1, the limit as x goes to -1 does not exist, and therefore it's not continuous. Okay, because these two pieces, this piece and this piece, don't connect, and therefore it's not continuous. So it already fails at the first step, and you only need one failure of a step to say it's not continuous. Okay, the next one we looked at was 0. Okay, so at 0, we actually we don't have any breaks or anything of that nature. So at 0, it is going to be continuous. Okay, at x equals 2, the limit as x goes to 2 is going to be equal to 5, but f of 2 is equal to 3, okay, because f of 2 is down here. So the limit's up here, at 5, but the point is down here at 3. Okay, so since these don't equal each other, then it's not continuous at 2. And then the last one is 4. We would say the limit as x goes to 4 does not exist. Okay, therefore it's not continuous at x equals 4. Okay, so you do need to recognize not just that you pick your pencil up to go from one place to the other, but actually why, like which of those 3 criteria is not being satisfied. Okay, so it says use the definition of continuity to discuss the continuity of the function at the indicated point. Okay, so basically you're wanting to go through the three steps for the definition of continuity. So if we look at the limit as x goes to 4, first of all, you should recognize that this is just a line with a y-intercept of 3 and a slope of 1. So a line is going to be continuous, but we do need to discuss these steps. So if I put 4 into it, that's going to be 4 plus 3 will give me 7. So the limit is going to be 7. F of 4, that's going to be 4 plus 3, so that's also going to be 7. And then since the limit of f of x is equal to f of 4, it's continuous at 4. Okay, use the definition of continuity to discuss the continuity of the function at the indicated point. Okay, so if I look at this, what I see is I definitely see that -3 is going to make that denominator be 0. So there is definitely going to be a point of discontinuity there. It's just a matter of which one of the steps it's going to fail on. So if we look at the first one, if we look at the limit as x goes to -3 of this, okay, so that's going to be 0 over 0, which is our indeterminate form. So let's look at if we were to factor it, which is what we do with the indeterminates, try to factor them. Okay, so here we get that common factor. So if I look at the limit, if I plug -3 in and take that limit, that's going to give me -6. Okay. If I look at what the function value in this case, is g, not f. So g of -3. If I try to plug -3 into that equation, that's going to give me, as I've already done, 0 over 0. So this is an undefined point here. And so that is ultimately the reason is that g of -3 is not defined. Okay, same idea here. H of 1 is going to give the situation of 0 over 0. So it's going to be undefined. So that would be reason number 2, that it's undefined. Therefore, it's not continuous. So be careful that you actually say what it is that you are trying to show, because just to say that h of 1 is undefined doesn't really connect it back to say that it's not continuous. Okay, this one is very similar to what we did before. This is just a line. So if we look at the limit as x goes to 1 of x plus 1, that's going to be 2. F of 1 is also 2. And since those two are equal to each other, we could say therefore it is continuous at x equals 1. This one, if we look at it, you can try, it would have a limit, but if you look at g of 1 would be 1 minus 1 over 1 minus 1, so 0 over 0. So g of 1 is undefined, so it's not continuous due to it being undefined at, it's not continuous at X. Okay, on on this one, if we plug 2 in, we see that 2 that is not defined because we get 0 in the denominator. And so it's definitely a discontinuity at X equals 2. Okay, we're not really as sure about X equals 0, so we need to go through those steps. So if I look at the limit as X goes to 0 of X minus 2 over absolute value of X minus 2, then what I'm going to end up with is negative 2 over 2. So I'm going to end up with negative 1. Also, if I look at H of 0, okay, if I look at H of 0, that's just plugging 0 into the function. So I end up with 1, and this one should have been 1 as well. So because they equal each other, I could say, therefore, it is continuous at X equals 0. So if you look at the graph on this one, over here at 2, you end up with a graph that's down here at negative 1 that looks like this, and then jumps up here to 1. So there is a break in the graph at 2, but there's not a break in the graph at 0, and that's why it is continuous at X equals 0, but it was not a point of but it was not continuous at 2. So just to be clear, it is continuous at 0. It is not continuous at 2. Okay, just a couple other things here. You've got a function said to be continuous on the right. So it can just be continuous on one side. So it can be continuous on the right if you've got a right-hand limit is equal to the function value itself. It can be continuous on the left if the left-hand limit is equal to the function value. And it's said to be continuous on the closed interval a to b if x at x equals c, if it's continuous on the open interval, and it is continuous both on the right at a and on the left at b. So you can be continuous and include those endpoints if the limit and that particular endpoint are equal to each other. So a couple properties, two functions are continuous on the same interval. If two functions are continuous on the same interval, then their sum, difference, product, and quotient are continuous on the same interval, except for values of x that make the denominator 0. And that's just kind of makes sense. Okay. So looking at a few of these, you've got a constant function would be continuous. X to the nth would be continuous. A polynomial is continuous. A rational function is continuous except where the denominator is equal to 0. If you've got the radicals here, then if n is odd and greater than 1, it's continuous wherever f of x is continuous. If it's an even function, then it's is continuous wherever f of x is continuous and also non-negative. So if it's an even degree function, then if it's an even degree index, then you need to make sure the function is positive for everywhere that you're looking. Okay, so this particular one, if we're looking at this one, is a polynomial. So a polynomial is going to be continuous for all x values. Okay, this one, if we're looking to see where it's continuous, this is a rational function, so it is not going to be continuous where the denominator is 0. So that's going to be at x equals 3 and also at x equals -1. So that's it's continuous for all x except 3 and -1. Okay, if we're looking at this one, determine where the function is continuous. So this is an odd index. So an odd index is going to be continuous for all x values. Okay, so we have a polynomial under here. That polynomial is continuous for all x. And since this is an index that's odd, then it means f is continuous for all x as well. Okay, this one has an even index. Okay, so it's going to be continuous for all values of x for which this is non-negative. So as long as x plus 1 is positive or 0, then these are the values for which the function is going to be continuous. So it would be continuous for all x such that x is greater than or equal to -1. Okay, there's a few for you to practice. This one, because it's a polynomial again, would be continuous for all x. This one is a rational function, so it's continuous except where the denominator is equal to 0. So that's going to be -1 and 4. So it's continuous except -1 and 4. Okay, this one has an even index, so as long as this is non-negative, which means greater than or equal to 0. So this would be continuous for all x such that x is greater than or equal to 4. This one has an odd index, and this is a polynomial that's continuous for all x, so that means that f of x is continuous for all x.